So geometry and physics have indeed a very long history together, many interactions over the centuries. And this lecture discusses a sample of such instances. And some of them are not only inspiration, but also missed opportunities. And this is a concept which I think we need to think about. And of course, I thought, partly because of the title, but because of the circumstance, it was adequate that I take a very historical point of view. And so the plan that I offer is to go back to Bernhard Riemann in the middle of the 19th century, who developed Riemannian geometry, as we know. I'm going to use relativity and special and general relativity as an example of the cradle of the new geometry. Then I will talk a little bit on how the concept of Ricci flow appeared. Then talk about gauge theories, which are theories in theoretical physics, which have developed over the 20th century, but played a very important role in the second part of the 20th century. And I will finish by Chern-Simon's theory, which started basically in the early 1970s, but now is everywhere in physics in some way, as I will try to show. And then I will conclude with 2 quotes from quite famous people. So let me start with Riemann. So as you know, Riemann defended his habilitation on the 10th of June, 1854. The document was published only after his death. And as you know, Riemann died quite young of tuberculosis. And the topic was typically in the German tradition that it was really not his work, but a topic that was chosen by the jury among 3 topics that he had the list ahead of time. So in a sense, the consequence of this, and of course it's Gauss, who was member of the jury, who chose the topic, which is Hypothesen, welche der Geometrie zugrunde liegen, which means assumptions on which geometry is based. So in a sense, this essay, which is extraordinary, was really produced in a very short time. Of course, it was not completely foreign to Riemann, who was thinking about such topics, but anyway. So, as the title says, it's talking about geometry, but there's absolutely no figures, and the whole document contains only one formula, without much explanation how the formula comes about, which is the formula for the Riemann curvature tensor. One thing which usually is forgotten, and it should not be forgotten for me, in particular in relation with the topic of my lecture, in the very last part, which is called Application on Space, and space meant really the space around us, Bernhard Riemann discussed the relevance of his considerations both to several parts of physics, to astronomy, the very large, but also there is a paragraph on the very small, which I think is not so. Actually, Riemann at that time was thinking a lot about the ether, which should be the background on which everything was moving. And also one thing which should be stressed, that he discusses explicitly the relevance of the concept that he has introduced, that is the notion of a Riemannian metric, a metric whose coefficients depend on the point, to consider both continuous and discrete settings, which for the time was not completely normal. And also he cares about whether the new concepts of Riemannian manifold can be approached by actual measurements. So in a sense, implicit in this document, there is consideration that it should be relevant for physics. And then later on, so as I said, in Riemann's document, there is the formula for the Riemannian curvature, but there is no trace how he came about it. The only trace is actually a project is submitted to the French Academy of Science about really discussing the propagation of heat in a medium, and in the notes that he prepared for this presentation, actually you can see some sign of what led him to the Riemann curvature. By the way, he didn't get the prize of the French Academy. Anyway, so The people who later developed really his ideas conceptually were Gregorio Ricci-Curbastro and not so much Christoffel. Christoffel, of course, is quoted for notations which are used in Riemannian geometry all the time, but it was just a shorthand notation for something which was coming up a number of times in one of his articles, but not the concept. So I'm really stressing the importance of Gregorio Ricci-Curbastro, which I think has been a bit underestimated. And he published a number of papers in this period, 1888, 1892. I gave the dates because very often we attribute to his student Tullio Levi-Civita, who was also a great scientist, a number of things which were really Ricci-Curbastro. Because in this period, Levi-Civita was not really productive from the point of view of research. So anyway, the first article I quote is this article in 1888 about covariant derivative, and then which is further developed actually in French in the Bulletin des Sciences Mathématiques. And then, of course, a document which is very often presented as an important summary is this article with Tullio Levi-Civita, long, systematic, which is called Méthode du calcul différentiel absolu et leurs applications, Method of Absolute Differential Calculus and Applications, which appeared in Mathematicians in 1900, and which is a very systematic, it's almost like a course. I mean, you can really use it as a document for a course. Anyway, so that's what I wanted to say. So here is one of the publications of Ricci. I said 4, so I listed 2. This is one of the other. And here you see explicitly discussing these metrics with the coefficients and the differentials. And that's what he called the form differentielle quadratic differential forms in n variables. And he really stresses everything you can deliver. So this was my first part on introducing the role and the way the Riemannian geometry was conceived by Riemann, really also with physics in mind. Although it's implicit, it's not very, but it's very much there. So as you know, I mean, there was this annus mirabilis 1905, where Albert Einstein published 4 fundamental papers, which changed physics in many ways. So in particular, one of these papers introduced special relativity, and it was really the reflection on the Michelson-Morley experiments led to the idea that the speed of light should be an absolute, should not be a quantity which depends on the means. So typically, what really led him to this, from the point of view of the formulation, is the various formulas from Hendrik Lorentz, which actually were making it quite explicit that space and time cannot be considered separate entities as they are in the theory of Newton. And these considerations were really taken up by 2 mathematicians, Henri Poincaré and Hermann Minkowski, in different ways. So in the case of Poincaré, it's in an article which is called Le mouvement de l'électron, the motion of the electron, published in Italy. And then it just shows that if you look at the group of invariants, which is preserves the transformation that Poincaré has been provided, it's the group of invariants of a bilinear form, but which has, he was talking about 4-dimensional space, which has signature plus, 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 minus. So that's what I call the cradle of a new geometry. So this geometry, of course, mathematicians had considered bilinear forms of this type, but this was really at the heart of the new thing. In the case of Minkowski, in a sense, his approach, in particular, which is in notes from a public lecture he gave, and the style of the lecture by Hermann Minkowski, who actually had been a teacher of Einstein at ETH, is very much in the spirit of Euclid's Elements, very axiomatic, and the text that he published is called Raum und Zeit, Space and Time, And he is really the one who, in a sense, coined the name space-time. So before that, it was not really there. And it's interesting that, of course, that was the first step, special relativity. But then there is a next step, which is, of course, general relativity. And it's very interesting to see that in 1913, Albert Einstein and Marcel Grossmann, one of his closest friends, they were students together at ETH. Actually, Grossmann played a key role for Einstein to come to ETH because, as you know, he had difficulty finding a job. When he was working for the Office of Patents in Bern, it was also partly because he couldn't find a job. Interesting to see. And they introduced a theory of general relativity. And actually, it's really, from the point of view of epistemology, a major jump. Because the key transformation is to replace the scalar potential, classical in the theory of gravitation by Newton, by a two-tensor field, which actually is the metric of the type which I mentioned, measuring generalized length. And the idea being that if you have the signature which I mentioned, plus, 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 minus, there will be some vectors which will be null, this whose evaluation of the quantic form of them will be 0. And these are the ones which are tangent to the light cone in this four-dimensional space. So that was the big shift. But the main difficulty, of course, so it shows that if you look at for such a metric, signature plus, 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 minus with constant coefficient, then this geometry is Minkowskian geometry in the same way as we are used to Euclidean geometry. But in a sense, what they were proposing is to jump from Riemannian geometry to Lorentzian geometry. That is to having, with variable coefficient, a metric of signature 3 plus 1 minus. And it's interesting to see that I'm quoting this 1913 date because they published in the Annalen der Physik 2 articles, one by Einstein, one by Marcel Grossmann, back to back, and one called, both of them, they are talking about the birth of a new theory of gravitation, and one is called the mathematical part, and the other part is called the physical part. The weak point, and that's why quite often physicists say you should never mention that, is that the field equations are actually wrong. And they are wrong for a very deep reason, namely they are not fully covariant. And of course you expect that everything you produce to deal with this new type of geometry should be covariant. So it was the attempt was very legitimate because they came up with the right concept, but they couldn't get the equation immediately. And as you know, I mentioned that in his essay, Riemann mentioned the Riemann curvature tensor. And before I move on to the truly Einstein equations, I want to do a digression into the Ricci curvature. And so the Riemann curvature tensor is, from the mathematical point of view, a complicated object. That's a 4 tensor, so something quite involved. And it's, of course, fundamental in Riemannian geometry because it measures the deviation of a metric from being Euclidean. So, of course, it's the fundamental invariant of Riemannian geometry. And it's very interesting because this object was very complicated, and people looked at it, and there were articles on it. But it took 50 years that people tried to extract from it something simpler, which is kind of very surprising. 50 years is a lot of time. And clearly, the new geometry was very important. And the person who made this jump was again Gregorio Ricci-Corbastro in a paper published in 1904 in the Atti del Real Istituto Veneto, which is called Directions and Principal Invariance in a General Manifold, and which introduced the Ricci curvature. So how does it define? Well, it's very simple. You have a Riemann curvature tensor, which is a 4 tensor, and you make out of it a 2 tensor by taking a trace. And if you use properly the variance of the Riemann curvature tensor, which spontaneously is a 3-1 tensor. Therefore, you can take the trace of the linear map, which to a vector associates R Z X Y, which is again a vector. And then, of course, now it becomes bilinear in X and Y. And because of the symmetries of the curvature tensor, actually it's not only bilinear, but it's bilinear and symmetric. So this is the birth of the Ricci curvature. The motivation of Ricci-Gubastro is interesting. His idea was to say, with this symmetric tensor, since I have a metric, I can also transform it into an endomorphism, and then I will have the principal directions. And actually, it was mimicking what's happening with the hypersurface, where you have the second fundamental form, for which you look at the principal curvatures. But actually, it's so the idea was to introduce some kind of privileged directions at each point, looking at the eigen directions of the Ricci tensor. But it's interesting that it didn't play any role geometrically. So in a sense, it's fantastic that Ricci introduced this object, which became so important in geometry. But actually, the motivation was not the right one. And it didn't lead to anything. Later on, of course, the Ricci curvature became very central. And again, it became central in relation with the general relativity. And actually, the field equations for general relativity were found in 1915 in a very interesting joint sustained effort between Einstein and David Hilbert. So it's interesting to read in the letters that you can find the exchange more or less. You could notice that usually they would write 1 week later for what they have found the week before. So they were giving some degrees of freedom to move forward. And so it's very difficult to know who is the first one to have found. Anyway, the way it goes is the following one. In physics, what is most of the time very important is to identify a good Lagrangian for your theory. So here the potential is this metric, this Lorentzian metric, and then you attach to a Lorentzian metric a function, which is what I call capital S, which is the integral of the scalar curvature measured against the volume element. And what is the scalar curvature? It's purely the trace of the Ricci curvature. So this is what you look, and then you look at critical points of this functional, the Euler-Lagrange equations of this functional. And what you find is that the equation for that is Ricci, R, which is there, minus a half the scalar curvature times G. So this is given by the gravitation. And in presence of other physical fields, you have a right-hand side, which we call the stress energy, which of course describes all the other types of physics which is present. If you're in the vacuum, of course, you take T identically 0. It's interesting that Einstein called the left-hand side made of imperishable marmor, that's the geometric part, and he calls the right-hand side of inferior wood, which was more or less cooked up for each kind of theory you want, electromagnetism, fluid, and so on. Anyway, and of course, this equation to be solved, so this is a set of equations, the unknown is G, and of course you want to solve this equation. Even in the case T equals 0, it's a very hard problem. And so Einstein equation have been approached in various ways. By the way, I want to recall and go back again to a paper by William Kingdon Clifford in 1876. And it's very interesting. Of course, Clifford is known today in algebra with the type of algebras which bear his name, the Clifford algebras. But in a note published in 1876, which is called On the Space Theory of Matter, here is what he says, which is clearly an anticipation of general relativity. So I wish here to indicate a manner in which these speculations may be applied to the investigation of physical problems. I hold. And then comes 4 points. Point 1, that small portions of space are in fact analogous to little hills on the surface, which is on the average flat, namely that the ordinary laws of geometry are not valid in them, which more or less suggests that actually what is really relevant for gravitation is the modification of the geometry, which of course at that time nobody was talking about that. Second point, that this property of being curved or distorted is continually being passed on from one portion of space to another after the manner of a wave. Third point, that this variation of the curvature of space is what really happens in that phenomenon which we call the motion of matter, whether ponderable or ethereal. So this is still a time where people were wondering whether there is ether, that is some kind of a background on which everything really is relying on. And last but not least, that in this physical world, nothing else takes place but this variation subject to the law of continuity. This note is absolutely extraordinary. You probably know that Clifford died also very young, I think it was 34, also from tuberculosis. So Riemann tried to cure his tuberculosis in Italy, but Clifford tried to cure his tuberculosis in Madeira, in Portugal. Anyway, so now I'm coming back to what was the discovery or the invention of Hilbert and Einstein. Why did they pick this functional, which is the total scalar curvature, by capital S? And since the middle of the 19th century, it was known that if you are in 2 dimensions, the functional S on the space of Riemannian metrics on the surface is actually constant. Indeed, if you are looking for a compact surface without boundary, then this functional gives you 2 pi times the Euler characteristic. So it doesn't depend on the metric on the surface. And so that was something known from Gauss and Bonnet. And actually, it's very interesting from the mathematical point of view that, of course, if you go in other dimension, it's not anymore true that this is a constant, but it has a consequence from the mathematical point of view, which is very important. You know, when you look at this functional, one thing you worry about is that the scalar curvature contains second-order derivatives of the metric. Therefore, when you do the calculus of variations, the equation you should get should be 4th order, because you integrate by part twice, and you should get the equation will be 4th order. But I gave you the Einstein-Hilbert equation, which is Ricci equals something, which means second order in the metric equal the physics, and therefore it's not 4th order. And this is the consequence of the fact that in 2 dimensions, actually the integral is, the functional is actually a constant. So it's a very interesting situation. So in a sense, this is what makes the total scalar curvature really special. And now, of course, the key point now that you have the field equation for general relativity, you want to solve it. And so actually one thing which was quite remarkable is the work of Schwarzschild, who very soon after the publication of the equation found some special solutions, and the so-called Schwarzschild metric, and not just any solution, because it is typically the metric which is produced by a star which is spherically symmetric outside the star. So in a sense, it provides a good model of the solar system. And therefore, for example, it allowed to check and provide, in the context of general relativity, a measurement of the advancement of Mercury's perihelion, which was actually checked for with an eclipse in 1919. So it was really interesting to have this model of Schwarzschild very soon. Actually, other special solutions have been found very soon. There are some which have been given by Willem de Sitter, for example. It is only in 1951 that Yvonne Breuer, she married Gustave Choquet later, so at that time she was called Breuer-Furès, who in 1951 made the breakthrough to give a general solution local in time and space to the Einstein equations. So the Einstein equations is a system of partial differential equation of second order, and which of course is equivariant under the group of diffeomorphism. So from the point of view of analysis, very difficult. And this is an extraordinary achievement which she managed to do using the most recent advancement, mathematical advancement by Jean Loret. Of course, great progress have been made on solving the Einstein equation, giving not only local solution in time and space, but also some global solutions. And I mentioned in particular the extraordinary work in the 1990s by Demetrios Christodoulou and Sergio Kleinemann, but later on there have been many, many other. And difficulty with these papers about solving the Einstein equation is that these are typically long papers. I was, for example, one of the referees of the Christodoulou-Kleinemann paper. I don't know whether I should call it paper. It was 463 pages. So it took me a year to do that. We were 8 referees, so all of us took typically a year to read all this. Now we are more or less at the situation where papers of this type are 100, 150 pages. So it's a big progress from the beginning. Anyway, I want to show a very interesting missed opportunity connected to this. In the late 30s, people were considering that the Lagrangian, which had been used to get the Einstein-Hilbert equation, maybe were not enough because there were some physical phenomena which could not be properly presented with this Lagrangian. So Cornelius Lanczos got interested in looking at other Lagrangian than the usual one. So you've seen that the Lagrangian with the total scalar curvature is a linear function of the curvature. So when you're in dimension 4, so in dimension 4 you looked at quadratic functions of the curvature. It's easy to prove that there are only 3 quadratic forms on the space of curvatures which are meaningful. And therefore, you can write them like this: the norm of the curvature, the Riemann curvature tensor, the norm of the Ricci tensor, the square norms, and the square of the scalar curvature. And then the thing which was noticed by Cornelius Lanczos and published by Cornelius Lanczos, if you choose the coefficient alpha, beta, gamma well, then the functional that you have here does not generate any field equation. It's independent of the metric. His conclusion was to say this Lagrangian is no good. Of course, as a mathematician, it's different. It's wonderful. You have found a new invariant of 4-dimensional manifolds. But that's not what he writes. And indeed, if you take the coefficient alpha equal 1, beta minus 1/4, and gamma equal 1, then you get, again, the Euler characteristic in 4 dimensions with a coefficient 8 pi squared. What is kind of amazing is that the article by Cornelius Lanczos was published in the Annals of Mathematics, actually in a volume which contains the first article ever published by Chen Chen. And it's interesting that it's only in 1944, so the publication by Lanczos was, I think, 1936. Chen published his groundbreaking article, A New Intrinsic Proof of the Gauss-Bonnet Theorem, that led to the theory of characteristic classes, again in Annals of Mathematics. The all new idea, I'm going to talk about Kaluza-Klein later, was going to the frame bundle. And there exists a formula for the Euler characteristic in dimension 2n. So we saw the one in dimension 2, the one in dimension 4, but there is one in all even dimension in terms of polynomials in the curvature of degree n. So you've seen linear for dimension 2, quadratic for dimension 4, and it goes on. And actually, I was very surprised to realize, talking to Chen, that he actually never heard of the Lanczos paper. And of course, Chen rediscovered the Lanczos identity. So now I'm moving on the way to the Ricci flow. There will be some equations, but you should not be afraid of the equation because I'm going to use them in a very light way. So just a warning. So actually, to solve the Einstein equation, one way which has been the most efficient way, in a sense, is the so-called Arnovit-Deser-Missner approach. Actually, it was first suggested by Yvonne Choquet-Bruat, then I can say Choquet-Bruat because then she was married to Gustave Choquet. So you can write the four-dimensional Lorentzian geometry in the following way. You can write it as a curve of a metric induced on a space-like hypersurface, three-dimensional hypersurface. And of course, since the hypersurface is space-like, GT is a Riemannian metric on the three-dimensional space. KT is the second fundamental form of this hypersurface. And phi t is the Leibniz function, which more or less, really encodes how the time is changing. And the Einstein equation takes the form of evolution equations, that is the evolution of the metric, which of course gives you back the second fundamental form. That's a traditional equation. Again, as I said, the Leibniz function encodes the evolution of the time. So if I divide by t, if I look derivative in t, of course phi t is appearing. And then also the next equation is how the second fundamental form evolves. But also it contains some constraint equation, which forget about them. They are there, very important, critical, but I am not going to discuss them. Actually, it's very important that if you, again, staying in the Arnovit-Deser-Missner setting, if I take the Leibniz function to be 1, if you look back at the equation and look what they mean, and bring them to really to a second order in the metric. So I combined the first two equations. You remember I had two equations, and I can really now use the fact that if phi is 1, kt is just the derivative of the metric up to a coefficient. And so actually you get that the second derivative of the metric is minus 3t plus some extra terms, but which are first order, they are not second order. So the leading second order term in the Einstein equation, if you fix the Leibniz function to be 1, is minus 3g. Therefore, it suggests to consider differential equations involving the Ricci curvature in the space of Riemannian metrics. Remember, GT is a Riemannian metric on the three-dimensional space, in the three-dimensional hypersurface. And of course, it's simpler to consider first derivative rather than second derivative. And actually, Thierry Aubin did that in 1970. He deformed the metric in the direction of its curvature to improve the curvature. And the key formula is the following one. The way the scalar curvature evolves, if you modify the metric by the Ricci curvature, is the norm of Ricci squared minus the Laplacian of the scalar curvature. With the fact that if you're at a constant scalar curvature metric, the only thing which is left is norm of Ricci squared. So it improves the scalar curvature. And from that, I obtained the result that if you are at a metric which has constants, at a metric with constant scalar curvature 0, and if you know that the manifold has no metric of positive curvature, this metric scalar curvature 0 has actually Ricci curvature 0. You need the norm squared of Ricci to be absolutely 0 everywhere. So it's interesting and there are examples of manifolds for which you know they don't admit metrics of positive Ricci curvature, using the index theorem, for example. Anyway, so therefore this suggests to consider the Ricci flow equation, which is the evolution of the metric, three-dimensional, in my case here, it's a three-dimensional Riemannian metric against the Ricci curvature. Actually, this is what I did in the lecture in 1979 in Berlin. So this is one of the questions. So I jumped from 00 to 324. So of course there are several pages in between. And which is to say, does the local flow theorem hold for the vector fields? Well, more generally, not just Ricci, but with also multiple scalar curvature on the space of metrics. And what is the global behavior of the integral curves? And so showing that this flow equation, which I'm asking about, as a local solution in the space of metric requires to resolve a system of nonlinear PDEs which is degenerate from the point of view of analysis. If you look at the expression of the Ricci curvature in terms of the metric, you see the combination of second-order derivatives of the metric automatically shows that every direction is actually characteristic. So from the point of view of analysis, it's bad news. Therefore, you know you have trouble. Therefore, you need to normalize in some way. And this was done by Richard Hamilton and Dennis Diterk in the early 1980s, working in a specific gauge, which has the advantage of killing the indefinity, which is connected to the fact that the principal symbol has a number of characteristic directions. Of course, to show that global solutions exist requires to make geometric assumptions, and this was done in a series of a remarkable paper by Richard Hamilton. And the rest is history. As you know, Grisha Perelman really pushed that much further. In my third paragraph, I mentioned that if you make the right geometric assumptions, then you can prove there is no singularity. But actually what Perelman did is that you can allow singularities, provided you're able to go beyond the singularity. And so he managed to do that in a remarkable way, and this led him to the solution of the Poincaré conjecture. Later on, I mean, the Ricci flow has found many applications in many fields. Now I'm moving to gauge theories. So I moved back to 1917 because, of course, when people had this equation for general relativity, so this was dealing with gravitation. But the question was, how can you combine this with other physical interactions like electromagnetism? And 1917, one of the proposals to unify gravitation and electromagnetism was made by Hermann Weyl. Here is the sketch of Weyl's proposal, which is actually very important conceptually because it was the first serious consideration of a so-called gauge theory, and it led to further understanding of the general concept of a covariant derivative, not necessarily a metric one, not only on the tangent bundle, but on the general bundle. And so the way the proposal by Hermann Weyl was to introduce a scalar field, which actually was just a factor in front of the metric. So he was really interested in encoding electromagnetism as really the conformal factor in front of the metric. Actually, this didn't work from the physical point of view for various reasons, but of course, it forces him to look very seriously into conformal geometry, and in particular to identify that there is in the Riemann curvature tensor a piece which is basically invariant when you do a conformal change, which is now called the Weyl curvature tensor. And it's quite remarkable that this Weyl curvature tensor is exactly what is missing if you are considering only the Ricci curvature. So if you take the full Riemann curvature tensor, you have two pieces. One piece which is not sensitive to conformal changes, the Weyl curvature tensor, and the rest is Ricci, which is an interesting separation of interaction. But of course, a little bit later, Theodor Kaluza, who was in Berlin at that time, sent to Einstein another attempt to unify gravitation and electromagnetism. So it was a different idea. The idea was to say, well, space-time is four-dimensional, but why don't we consider a five-dimensional Lorentzian space, which means you add one dimension, which is, you remember, I want this to be Lorentzian, so 4 plus 1 minus. And so the metric will be called G twiddle in 5 dimensions. And there is an ansatz to relate the local expression of the G twiddle to the ordinary space-time metric in 4 dimensions and the electromagnetic potential psi, which, of course, has to be present to take care of electromagnetism. And the key formula that is the one that describes the 5-dimensional Ricci tensor in terms of this other data, that is G and psi combined in G twiddle. And the quite extraordinary feature that was noticed by Kaluza was the fact that if you write that the Ricci curvature of the 5-dimensional space is 0, then you get back both the Maxwell equation for psi and the right-coupled Einstein-Maxwell equation. That's the left-hand side in 4 dimensions is the Ricci minus 1/2 scalar curvature times G, and the right-hand side is what had been cooked up, inferior wood, as Einstein called it, for electromagnetism. So it's quite a remarkable fact. One thing which is interesting is that the first reaction of Einstein said, well, but this is no information. So he refused the publication of this note, and actually the postcards on which Einstein replies are available, and you can look at them and see. But finally, a few years later, I was told actually that Hermann Weyl played a role on this. Einstein accepted to publish Kaluza remark, which is quite extraordinary, I mean, in terms of efficiency of the coupling of the equations. And it's very interesting that what lies behind the computation of the Ricci curvature of this 5-dimensional metric with the ansatz used by Kaluza is that it's very much the general formulas for computing the curvature of Riemannian submersions, which had been done 40 years later by Barrett O'Neill. And nobody cared about that. Mathematicians were very much impressed by submanifolds, but submersions have been forgotten for a long time. Although it's not more difficult, but it was not taken seriously. So now I move on with the gauge theories, because in the 20th century, gauge theories kept reappearing. In the 1950s, of course, people were looking for classical theories which would be able to produce some quantum perturbation. And so that's the work of Yang Chen-Ning and Robert Mills. So they proposed a non-abelian gauge theory. So a classical theory, you will have just a Lagrangian, as the Lagrangian we have been considering. And with the idea that if you look at them properly, you are going to provide some value for the quantum perturbation. And the groups they had in mind, that's why it's non-abelian, are the group of invariants for the strong and the weak interactions. So SU3 and SU2. And then the whole setting is that of a G bundle, G being the group of symmetry of the interaction under study, and the conditions of the experiment being incorporated in its description. A typical example of this, which was a thought experiment, imagine you have really a circulation of electricity which really forbids a region, and then you have a particle which goes around this wire, and you look at the interaction between for this beam going around the wire when it goes back, and then of course that's what I call the conditions of the experiment. Because of the presence of the wire, going around is not the same thing as being outside the wire. And therefore, one important variance is the number of turns that you make around the wire. So this so-called Aharonov-Bohm experiment. And this can be, and then what do you take as potential, as we use the metric as potential, is the G connection on this bundle. And then the Lagrangian that you take is the norm squared of the curvature, which of course is a first order derivative of the connection. And so you take the L2 norm of the curvature, and then the field equations are nonlinear if the group is non-abelian. And of course, this is, so the theory a priori should be done on space-time. But actually, the idea which has been dominating, and actually a very important impact, was to do a so-called shift on the time by taking the time purely imaginary. If you do this, of course, the Lorentzian metric becomes Riemannian, and therefore your space-time is not anymore space-time because you have done a weak rotation, as we call it, and it becomes a Riemannian metric. And therefore, among the very special solutions in 4 dimensions, that you can find are the ones which are actually contain first-order derivative of the connection, the so-called self-dual or anti-self-dual connection. When, of course, the equation for normal equation are second order in the connection. And so actually, one typical example where this idea of the physicists to consider these special solutions that they call instantons. So instantons partly because they have gone from a Lorentzian to the Riemannian setting, and has produced fantastic results from the mathematical point of view. So this is a typical example of a source of inspiration. So the understanding of the most fundamental spaces in dimension 4, such as the R4, resisted a long time to topologists. A number of questions on the fundamental invariant of compact four-dimensional topological and differential manifolds, the signature form, which is a form on the two-dimensional cohomology, remain open. And instantons, which are these self-dual or anti-self-dual connections, which are objects of physical origin, allowed to the key breakthrough. In the background, there is the work by Michael Friedman, who showed that all topological manifolds homotopic to R4 are actually automatically homeomorphic. Where the breakthrough happens was done by Simon Donaldson, that is actually by attaching to any compact-oriented differentiable four manifold a completely new type of invariance, namely the spaces of SU2 instantons, that is self-dual connection, and bundles over it. Then, from this consideration, he was able to show that R4 has infinitely, and actually with a with a continuous power, infinitely meaning non-equivalent differentiable structures, which was an incredible achievement and a big surprise, because you imagine R4 should be R4, very simple. It was not at all, and for the moment, very few of them, I think there is no really explicit description of any of them, which I think is something very impressive. I'm moving now to Chern-Simons theory, quickly. So actually, it's again around this issue of understanding some invariant of four manifolds. So Jim Simons and many topologists had been obsessed with the idea of finding a combinatorial formula for the signature of a four-dimensional manifold. And then he realized that actually there is if you look around the point, and really the thing which prevents you from giving the combinatorial formula is a certain three form on the boundary of the star of a point, which is typically a three sphere. And so this was the starting point of Chern-Simons theory. So if you take a G bundle on the three manifold, which is endowed with the connection with local form is A, the Chern-Simons three form, CSA, is 1/4, and then you have A wedge dA, which is a three form, because A as a local form of the connection, of course, is a one form, taking value in the Lie algebra of the group. And then the second term is 2/3 of A wedge A. And then the bar denotes the suitably normalized killing form on the Lie algebra. So this was the work of Simons in 3 dimensions, because he was working on this problem of finding a combinatorial formula for the signature of a four manifold. But of course, Chern helped Simons to extend this to all odd-dimensional manifolds and developing really the theory of secondary characteristic classes. Then the key remark, which really, after that, had been fantastic development, was the creation of a Chern-Simons functional, because actually using a section from the manifold to the bundle, you can really integrate the Chern-Simons form, but you have to be careful, because if you are, depending how you use it, you actually can change the value of the integral by a multiple of, by an integer, which means that the functional that you get is actually only function taking its value in R mod Z. Of course, if you're interested in the exponential of this quantity with I in front of it, you don't care, because, of course, the fact that you have ambiguity by Z gives you just a multiple of 1. And so this is this Chern-Simons functional, which has really been very successful. So it inspired many physicists, and well, I could have listed many things. I'm going to list a few things, but I could have listed many more. After initial input from Bertrand Halperin, Jörg Fröhlich showed how the Chern-Simons theory can give you a very good description of the quantum Hall effect and also the fractional Hall effect. So this is the three-dimensional Chern-Simons. But also, you can also have another presentation using dimensional reduction, using a five-dimensional Chern-Simons. Using it, Witten showed how to connect Chern-Simons theory to John's polynomial of knots, also developing a relation to quantum groups and Gromov-Witten invariants. Witten also showed how, in the context of string theory, also the quantum theory of many body systems, you can actually use the Chern-Simons theory. It also found use in the study of hydrodynamics. I'm going to quote from a long list of things that Nikita Nekrasov provided. He provided a survey of the contribution of Jim Simons to Chern-Simons theory, and he lists a number of these. So here I'm listing some of I extract from the list of Nikita a number of uses by physicists of Chern-Simons theory. So relation to contact structures, a role in the study of supergravity, a relation of Chern-Simons theory with two-dimensional conformal theory, and an approach involving Chern-Simons theory to study the Knižničná logic of Bernard equations and geometric quantization, critical values of Chern-Simons function with polylogarithm, which actually led to very interesting new mathematical development, and so on and so on. So it's a very impressive developments from something which was purely motivated by a mathematical question and later developed by physicists in many different directions. So I'm coming to my conclusion. So my concluding remarks is to say that I could have followed many other paths, so I give some examples. After the identification by Élie Cartan of spinors in 1814, they became central objects in physics in the context of quantum mechanics with the introduction of Dirac Operator by Paul-Adrien Maurice Dirac in 1926. Although Élie Cartan made major efforts to have spinors adopted by mathematicians, adopted in mathematics, actually followed by André Lichnowitz, it is through the work of Michael Atiyah and Isago Singer on the index theorem that this finally appeared. The reason being that the Dirac operator is, in a sense, generates all possible elliptic operators, and this is really the reason. Of course, Calabi-Yau metrics, which are very specific Kählerian metrics with a zero Ricci curvature, are now a very central object in theoretical physics, in particular in complex dimension 3, and actually they generated a number of results in algebraic geometry. And also, in this context of this theory in theoretical physics, connected to actually the use also of Calabi-Yau metrics, and there is the occurrence of the so-called mirror symmetry, which associates the complex geometry and Calabi-Yau geometry, led Maxim Kontsevich to new geometric approaches involving higher order category. I'm finishing with two quotes. So the first quote is in a letter to the physicist Arnold Sommerfeld in 1912. So I told you 1913 was the publication of the generalization of general relativity. So Albert Einstein writes, "I'm working exclusively on the problem of gravitation, and I think I can overcome all difficulties with the help of a mathematician friend here." He's in Zurich at that time, and of course the friend is Grossman. But one thing is certain, never in my life I've worked so hard, and I've gained enormous respect for mathematics, whose most subtle aspects I had previously in my naivety considered a mere luxury. Compared to this problem, the original theory of relativity is child's play. Interesting quote. The next quote is by a physicist, an extraordinary man, Freeman Dyson, who was professor at the Institute for Advanced Study. So he gave in 1972 the Gibbs lecture. And if you look at the people who gave the Gibbs lecture, it's a very impressive list. And so he entitled his lecture, Missed Opportunities. So here is the text which appeared in the bulletin of the American Mathematical Society. I'm going to read this text and comment on what comes after. I encourage you to read this paper, which is absolutely amazing. The purpose of the Gibbs lectures is officially defined as to enable the public and the academic community to become aware of the contribution that mathematics is making to present-day thinking and to modern civilization. This puts me in a difficult position. I happen to be a physicist who started life as a mathematician. As a working physicist, I'm acutely aware of the fact that the marriage between mathematics and physics, which was so enormously fruitful in past centuries, has recently ended in divorce, 1972. Discussing this divorce, the physicist Res Joost, who was in Zurich, remarked the other day, as usual in such affairs, one of the two parties has clearly got the worst of it. During the last 20 years, we have seen mathematics rushing ahead in the golden age of luxuriant growth, while theoretical physicists left on its own has become a little shabby and peevish. So I'm forced to give this lecture an emphasis different from that intended from the founders. Instead of talking about the contribution that mathematics is making to present-day thinking in my field, I shall talk about the contribution that mathematics ought to have made, but did not. I shall examine in details some examples of missed opportunities, occasions on which mathematicians and physicists lost chances of making discoveries by neglecting to talk each other. And so then the whole paper is dedicated to missed opportunities. And the first one is absolutely remarkable because he's talking about some work about young MacDonald, in which he was interested in the various number theoretical functions. And then it turns out that this work was done while young MacDonald was at the IAS in Princeton. That Freeman Dyson and Jan MacDonald had daughters of the same age, in the same class. They met to get their children out of school. They never talk about each other. And actually, both of them were doing the same thing at the same time in Princeton, but never spoke about it. And he discovered it only when young MacDonald had published his work. So we should never miss opportunities. Thank you very much.